The question I always get from people is, what is AI? It's where we always want to start. We think of these conscious beings and like, can we build that? The short answer is no, we can't. So what really prompted this presentation is that we get into such discussion about what are the basics and how do you define this, that we thought we should at least build a primer and simplify the whole idea and say, what is it we're actually doing and how does it apply to security? So my goal in the next 20 minutes is just to cover that. So the first thing is that the words artificial intelligence, machine learning, deep learning, they're all buzzwords in a sense, but they're real. They always get very muddled with crowds, and people have a hard time differentiating what's the difference between them. Quite simply, artificial intelligence is the output of what you're trying to do. The easiest way we always described it is that it's when a machine is trying to do things that humans like to do and it's a repetitive task. Now the thing about it is machine learning is a method and a means to AI, but it's not AI by itself. Back in the 80s, we used to use something called expert systems, which is quite literally an expert would go to a system and he would train it everything that he knew as a human. One of the early examples of that is when they built autopilot in airplanes. That actually was considered AI back in the 80s. But unfortunately, as humans, we're a very tough crowd, and what we think is AI is the moving definition. Then the last part is deep learning. So machine learning, what it is that where if an expert system, sorry about that, machine learning is the idea that early expert systems took a human to manually train a system and they had to teach every single step of the process. What we learned with machine learning is that we can train a machine by example. If we show a machine enough examples of a specific task, after a while it starts to understand that task and it can go start to do it itself. And then deep learning is simply just a subset of machine learning. So to break it apart a lot easier, so when we think of machine learning, there's three different things that we care about in particular for security. There's actually other examples, but what it really comes down to is supervised or unsupervised. Supervised is quite simply task-driven. The idea is that you give it a very specific thing to do. You give it an input, basically. You say, I have X data and I have Y output. So for supervised learning, you say, here's the data and here's what I expect from it, and you do it enough times that it learns what that task is, and with both data sets, it actually says, okay, I get it, let me go out there and start to learn this myself. With unsupervised learning, you have X but no Y. The idea is that you give it a set of data that here's my inputs, I don't know what the output is, and I want to learn from that. Now to simplify this, without getting into random forest clustering, things like that, what I really just want to do here is just give some human analogies, an example of each. And then deep learning, by the way, it could be supervised or unsupervised, it's just an application. Let me just simplify this. So if you think as a human, if you think about learning tasks, we actually do learning every day as humans. Everything you do, we do different things. And when you think of a machine, it's just trying to do what a human already does. This example here, this is what we call a decision tree. So if you think about your normal life, you're hungry. You ask yourself a question. It's lunch right now. Am I hungry? Yes or no? The answer is yes. Then you say, do I have $25? Yes, I do. Okay, so you go to a restaurant. If you say, no, I don't have $25, then you go to McDonald's. It's very cheap. You spend $5. Now imagine that I said that it's $25, but then you said you'll go to a restaurant if you had $15, or somebody else says I need $50. Everybody actually makes the decision, and every one of these is a decision tree. When you take lots of these decisions and you feed it to a machine, you actually have what they call a random forest. And it takes all this data and it takes the attributes of it, and if you look at this, it starts to say, I know you're going to a restaurant, I'm going to predict that because A, you're hungry, and B, you have $25. Now when you give it lots of decision trees, it starts to understand what the averages are. Like, you said 25, he said 15, he said 50. At some point, the machine starts to figure out the difference. And in that way, X, the input is, am I hungry, and Y, the output is, go to a restaurant. You taught it the decision that you're going to make to go to a restaurant. This is what we call classification. Regression is a different kind of learning. The idea is that you're trying to find basically a value. You're predicting a quantity. A good example of that is that if say you're going to buy a house, everybody does that, that you start to look at neighborhoods and you figure out the price of a house in this neighborhood is 10 times higher than the price of a house in that neighborhood. As a human, you're actually doing this regression model where you're shopping around neighborhoods first, and then you can predict that if you want to buy a house in the west side of London, it's going to cost more than buying on the east side. It's something very simple like that. That's the same thing we do for a machine when we want to predict where's the higher number going to be. Unsupervised learning is, the idea is effectively clustering. Probably one of the best examples of that is in advertising. When you go to advertising groups, if you think of marketing here, everybody knows their target profile. They go around, they look at people, like actually everybody in the office, everybody in this audience has already been clustered by a vendor. They've looked at you and decided, are you a buyer of my product? Why? Because this is your job, this is what you do, this is your industry, this is how many employees you have. There's all these values about you that they've took and put together, and they've put you into a group. And they say, this is a CISO at a finance industry, and it's a large bank with 10,000 clients. This is an interesting client to me. And then this is a guy to healthcare, and they treat you differently. The advertising agency does it, insurance agency does it, everybody does it. As humans, we actually do it. We call it stereotyping. When you look at people and you predict that if you see this guy and he looks like a gangster, you probably think he's a gangster. You've already made an opinion and a bias about him. That's actually what the machine does as well. The idea is that you just do it mathematically with unlabeled data, and it has to come to these decisions. So deep learning, real world example, is something that we talk about is called transfer learning. Now this is an interesting problem that computers had where so with machine learning, one of the biggest issues is that machines lack context. It's a very basic thing that humans can do. Whenever we have a conversation with somebody, we actually carry context from one sentence to the next. A perfect example of that is if somebody says, I grew up in France, the next sentence he would say, I'm very proficient at. Most humans can fill in the blank and say, I'm very proficient at French. Believe it or not, machines have a problem with that. And if you've ever used a voice assistant, you've already seen this. If you talk to Siri, for example, you'll notice that you can say, tell me a joke, it tells you a joke. And then you say, tell me another. It actually doesn't know what you mean by tell me another. There's no context to it, and you actually have to repeat your whole statement that says, tell me another joke. This has been a huge fundamental stopping block for machine learning with computers. So in the last few years, they've revolutionized this idea of what we call transfer learning, which is if you have a skill set, you could transfer it to something else. A very human example of that is if you're a tennis pro, you've learned to play tennis, a friend asks you to go play squash. It's kind of like tennis. It's close enough that you have a skill that you can easily pick up squash because it's about the same thing. This has been something that we've had to solve mathematically with machines, and they've applied deep learning to do this. So deep learning is a machine learning, but what the fundamental difference is and what we solve with it is that with all the other types of machine learning, both supervised and unsupervised, you require a human to label data, and they have to take these data sets. So when I talk about decision trees, and I say that you have all these things about being hungry, you actually need a data scientist to sit there and keep training the data and then train the data over and over. And if you think about large data sets and you need thousands of images or thousands of words, or you need lots of data to feed into it, there's actually a very manual process that limits the entire process of machine learning. And it's an irony that people don't realize, that machine learning is all about big data, but if you need a human, you slow down the process. So what we've been able to do with deep learning is take the human out of the equation of the data labeling, and therefore, instead of having a large data set, you can actually work with a smaller data set, and transfer learning allows you to take that small data set, learn certain things about it, which is a sample size, and then transfer that to other things. So what that helps us in security is that we don't know how attacks work, we don't know what people are going to do, and it's the issue we've dealt with signatures the entire time. It lets us take a certain amount of data, learn from that, and pass it on. So one comment about all this, and the reason we talk about all these things is that when you go to vendors, you should ask them. You should say, all right, what kind of machine learning are you doing? A lot of times they'll tell you, I have this algorithm. I do just supervised learning, or I use this. What we learned about that is that if you're truly building an AI system that replicates human tasks, using a single algorithm doesn't actually do the job, and it's not really AI. I candidly say that to people, and what I tell people is to ask the vendor for the numbers and the outputs. What human process are you replicating? If you're only detecting things and you have one algorithm, it's not really AI, it's just better detection. What we learned is that you have to have the right tool for the job, in the sense that supervised learning is very good at some things, just like in real world, but it's not very good at other things. So you actually have to look at the task you're trying to do, be that I want to know who administrates a system. That's a good use of supervised, unsupervised learning. But you're like, but I want to find a remote access Trojan or people trying to get on my network. That's a good use of supervised learning. And so when you start to look at how we apply this to security, you have to be very specific about what it is you're looking for and how you apply it. So that when somebody is using just one algorithm, they're actually very limited. It's kind of like trying to build a house with just a hammer. Everything has to become a nail. So going more down, so now the point is like, the idea is to cover the basics to say, so how does this help us with security? So for the entire life cycle of security, everything has been effectively some level of pattern matching, be it anomaly detection, or be it saying, I know exactly what it is. What we focused on heavily is saying, what is an attack, like what does an attacker look like, so to speak? If you took a piece of malware, we would say, this is the malware because it is that. What we're able to do with machine learning now is, instead of focusing on what something is, we focus more on what it does. So if you think of like the decision tree and say, I went to a restaurant, instead of trying to match the restaurant, you start to say, well, what are all the things that lead to that? Like, I was hungry, I had $25, and there was a restaurant, and I had a car. So you take all these attributes and you start to train the system on that, to the point that the machine is able now to start looking for the behaviors associated to an attack without knowing what the tools are, without knowing who the attacker is, where he came from, why he did it. None of that actually matters. The only thing you focus on is what they're actually doing, and they're doing it to you right now. So I want to just quickly give some real world examples of both supervised and unsupervised. But first, before that, I want to make one major point. The other thing about data science is that most data scientists are actually not security experts, and that if you only use data science by itself, you don't really solve a problem. You end up with just a statistical machine. So what we learned is that you have to always start with security research, and you have to start with a security researcher. There has to be a security expert in the room who can actually tell the data scientist what is it you're actually looking for and how does it work. Like, you have to teach them that. So the real trick here is to combine that security research around what is it we're doing with the data scientist who decides what's the right tool. A way to think of that is, if you think of the house, the security researcher is kind of like the architect. He tells them, hey, we're going to build a house, it needs to be a wood, it's square, this and that. And then the data scientist becomes the builder. He says, okay, that's what you want, I have a hammer, a screw, here's what I do, I'm going to build it for you. So I'm going to bring these together. So as a real world example, for external remote access, I mentioned it before. So this is an example of supervised learning, and specifically, this is an example of using deep learning with the transfer learning to do supervised learning. So if you think about remote access, the way people get into a network is that usually we think about there's some type of malware tool, but the reality is that external remote access could be your PC anywhere, go to my PC. It could be a WebEx. If you think about what it is, the behavior is that there's somebody on the outside controlling a system on the inside, and the idea is, how do I find that person regardless of what tool he is? So what's cool about deep learning is that we're able to take a subset of tools, which you see here. There's TeamViewer, Canvas, InOpen. There's a combination here of real tools used on your network, and then there's a combination of attacker tools. But we don't know every tool that an attacker wants to use. So what we're able to do is train the system on this subset of tools and say, this is what it looks like when somebody wants to get on your network. The machine learns enough of that, goes, okay, I get it, I see what they do. And so then when you apply it to the network and looks, instead of looking for TeamViewer, it actually just looks for any tool that tries to do the same type of behaviors, and you end up with tools like LogMeIn and JQ Snicker that we never saw before, but in this instance, it was able to learn that. And the idea here with the security research is the security researcher is telling the data scientists, here's what extra remote access looks like, here's the tools you need to do, here's the data sets. So, unsupervised learning. It's really good at learning how your network works locally in your context and what you do. So you start to think about who administrates systems, who logs on the networks, what is it that people actually do. In this case, the security research thinks about what is it an attacker actually would do once they're on the network, how do they propagate, how do they spread, how do they get onto a server. There's a combination of behaviors that actually go into this. And then the data scientist applies unsupervised learning, and the idea is, let me start to build these clusters of groups and say, what we call domains is that, here's a set of users, here's a set of servers. I start to understand that this guy, well, we could call him Jay. Let's say Jay administrates servers in London, and he lives in Munich. And we know that he does that at 8 in the morning, and we see the patterns around that, and it starts to learn that stuff, so that if we see Jay administering a server from New York in London, and he does it in the afternoon, that's an anomaly. That starts to become an unnormal behavior, or we see the account used twice. So unsupervised learning starts to learn those local contexts. So bringing it all together, so I mentioned that the real value of AI is when you start to replicate human tasks. The first examples we showed you were just detections. It's just a better way to detect. But ultimately what you want to get out of it is you want to reduce the workload of the actual human and make their jobs more efficient. So one of the hardest things in security is that most of the things out here try to detect things, but they don't do a good job of reducing the noise and starting to prioritize what is it you actually want to look at. So what we learned is that this is a really good problem to be solved with unsupervised learning. You can actually use Bayes probabilistic algorithms for an exact name for this. And the idea around this is that you can take different behaviors and start to associate them in such a way that an attack needs context, that if somebody got onto a server, it could be an admin or it could be an attacker. The question is, what did they do before or after they got on that server? Did they have some remote access? Did they start to scan other servers? Then they access the server, and then they stole data. That's actually what an attack looks like. And the idea behind all data science is all probability, and it's probabilistic math and statistics. So what you start to do is assign a threat uncertainty score to every single host, and you tell it that when I see a combination of all these behaviors, I have a 90% certainty that you have a problem, versus being black or white and say, I saw an alert, do you care? The question is, do you care? And you have to start mapping that out in such a way that things like adware, that's a low threat, low certainty. You don't really care about every machine that has clicked on something, but you do care about the people that are trying to steal your data. Sorry, I'm trying to hurry up through time. I think I'm running out of time here. So just another comment, a lot of people, so obviously a lot of people what they're trying to do is hire their own data scientists, hire their own security researchers, they want to build it themselves. One of the biggest issues we learned about it, and the hardest thing about data science isn't building the algorithm, it's actually having the data to train the algorithms on, and that's going to always be a big challenge. You got to ask yourself, how many people do you have, what are you competing against, things like that. I'm going to kind of jump forward and just make a more, I think it's an easier way to put it. So what this is our actual process internally at Vector on how we build algorithms. So when I talk about starting with a security researcher and then going to a data scientist, it's very specifically like this. Now, the comments I want to make about this is that, so we have 50 algorithms internally. The way we built this system is we have right about 50 algorithms completely. It's taken us 5 years to build those 50 algorithms with 30 people. It takes, at a minimum, 4 months to build a basic supervised algorithm. to look for, say, Tor traffic, that was 4 months of work. Most of our algorithms, especially the unsupervised, take over a year. And even then, you have to start rewriting algorithms and retuning them. The way we measure our algorithms is in an accuracy score that we could say, this algorithm 94% of the time gets it correct. And we look at these efficiency models of all these algorithms. And we're always constantly striving to improve these algorithms, sometimes by 1%. You might move from 94 to 95% year to year. So all I got to comment on is that if you want to build it yourself, you need to realize that you're going to go through this process roughly, no matter what you do. You might drop some of this stuff on the develop UI and all that, but you do have to go through this algorithmic development process, and it's a very ongoing process. Back to the floor. Obviously, I left this here because I'm really surprised at how many people walk around. It's like, it's tongue-in-cheek. Our booth says AI as well. It's what it is. That's the way it is now. And I even say this for us. For anybody you talk to, there's a subset of questions you want to ask them. And as I mentioned, start with asking them how much machine learning you're doing. I always joke with people that a junior data scientist and algorithm does not make AI. A lot of people are taking it and just applying it on top of what they do, but they haven't really done it fundamentally. How many algorithms do they have? What kinds are they using? Ask them, this is a big one, by the way. Number 3, the candid truth of it is that people say that if you put it into an AI or machine learning system, it's totally hands-off. That's not true. What you actually have to do is train the system. You might not be doing false positives, but you do have to train it, and it does have a learning period. For us, some of our unsupervised algorithms take 5 to 10 days before they work. You don't just put it in and it starts working. It actually has to take time to learn it. And the last one is pretty important too. And candidly, if AI is going to replicate a human task, it should create a workload reduction. Ask them what that is. Our number is 32x. I can give you very exacts if you were to ask me about it. And then the last slide, they're giving me the sign that I'm out of time here, is that, I think philosophically, we need to realize that machines aren't going to replace humans. In fact, in most instances that we applied AI, we've actually found that there was an increase in the number of humans working. What we've learned interestingly in security is that machines and humans are completely different. They always will be. Machines don't have a conscience. They don't wake up in the morning and say, why am I here? Why am I doing this? They don't do that. What machines are very good at is memorizing large amounts of data, being very repetitive tasks, and taking tedious work and starting to minimize that, and doing it really fast in real time and multitasking in the way that humans can't. Humans are very good at being creative and being very objective and looking things contextually. We're able to take very abstract ideas and make connections based on things we did or experienced or stuff we saw. So for security to actually work, it's not man or machine. All the results show that it's a combination of man and machine, each doing what they do best. The machine does a lot of the tedious work so that the humans can focus on the creative work. And with that, I think that's a thank you, and we're out of time. I don't know if there's any questions or I have even time for questions. She has the microphone back there. Are there any questions?
Hi, can you hear me? Do you take information or data out of your customer to train your systems, or where do you take your data to train them?
Yeah, that's actually an incredibly important thing. So back to the whole idea that the data set's important, what we've learned is the best way to train this is on real data, and we absolutely use live networks to train all our data. So I can't name some of the names, but some of these networks have millions of machines on it, and like, let's take just basic Kerberos stuff, basic authentication. You want to train that on real data to get the best value out of it. Not only do you train it on that, you have to constantly retune it and look back at it. So what we do is create this network effect where we collect metadata. So even after something's deployed, you constantly retrain it, and a data scientist is always involved in the loop to keep checking that data. The biggest scare we have in security is what we call data pollution, that somebody can manipulate the data in such a way to evade the machine so that they teach it that what you're looking at is actually what it's supposed to be, and you have to constantly check that.
In the human analogy, if you have a baby, eventually you can train that baby anything, play the guitar, speak languages. Is there something on the machine side that you have an algorithm and a machine, and with some diligence and patience you can teach that machine anything? Or is it only this thing is built to learn this thing is built to learn that? Is there some generic artificial intelligence?
So there's two kinds of AI, and we call it general AI and focused AI. What we're doing as an industry, candidly, is focused AI. Everything is task-based. It's very much task automation. What everybody talks about, what you are, is called general AI, and that's always been the dream of AI. We don't know how to do it. That's the honest truth. There's no one doing it. There's a lot of theory and research into it, but there's been no execution. No machine has been able to walk away and do any more than you taught it. So it is very much. And for us, that's why we have 50 algorithms. Every single algorithm does a very specific thing, and you have to combine them all. And so it's a whole bunch of tasks combined together. I think we're out of time now, so with that, thank you. If you have any more questions, our booth is D260. It's just straight over there. I'll be over there. I'm here now. Thank you.